Hey there, ladies and gentlemen, Mrs. Matheson here. We're going to be covering Unit 6, Notes 3 today on exponential decay. So very similar to our previous notes on exponential growth, our learning target is I can graph, model, and apply exponential decay functions. So big thing here is that we see that this exponential decay function looks very much so like growth, minus that it's going to be an minus problem. Our C is still our initial amount, R is still the rate of change expressed as a decimal, and T is still time. Also, don't forget our C value, that is going to be our y-intercept. All right, so let's go ahead and look at this first problem. It asks us to write it into an equation. So we have y equals our C value times 1 minus our rate as a decimal to the T. We're going to simplify inside the parentheses and get 16 times 0.55 to the T. Now, remember we talked about is that we can't take the 16 times the 0.55 because it's going to be following order of operations and we would do exponents first. We don't deal with X, we're going to deal with T, but I still ask you to do -2, -1, 0, 1, and 2. All right, so great thing here is we talked about we can plug this stuff into our calculator. Man, our life is a lot easier with those darn calculators. So we have 16 times 0.55 to the -2 power. Plugging that into our calculator, we're going to just round to 1 decimal place because remember we really can't graph that accurately to 2 decimal places. So we're going to get 52.9. Now we're going to plug in -1, so we get 16 times 0.55 to the -1 power. And this one is going to round to a 29.1 decimal place. Then we come to our 0, that's our y-intercept, which is our C value. And so our y is 16. Then we're going to plug in 16 times 0.55 to the 1 power. When we plug that into our calculator, we're going to get 8.8. And our last one is 16 times 0.55 to the 2nd power. We get 4.8. All right, so we're going to graph these on our graph over here. We're hoping to see that gentle curve again, but this time it's going to be going down. So -2, whoa, all the way up at 52. Can't graph that. -1, whoa, all the way up at 29. Can't graph that. We're okay with that. It's not a big deal. Then 0, we're going to be at 16. And 1, we're at 8.8, so almost to 9. And then 2, we're at 4.8, so almost to 5. So just because we have 3 points doesn't mean we can't still see that we're just starting to have a gentle curve. All right, and it's going down, so this is a decay function. All right, let's look at number 2 here. We have our C value, we have our R value, and it's that darn 1/3 again. So we have y equals our C value times 1 minus 1/3 to the T power. Now we can convert 1/3 into a decimal because that's what we said is that R needs to be as a decimal, but we would have 0.3. Let's see here. We would have y equals 15 times 1 minus 0.3 leaves us with 0.7 to the T power. Now we could leave it in our fraction of 2/3 because 2/3 is 6.6 repeating, which would round to 0.7. Okay, it's going to make a slight difference in our decimals in our y values, but not a significant difference. So remember our x is going to be t, and I want you guys to go ahead and take the time to fill in this chart. Use our same values that we have been using this entire chapter for the t. All right, check your values. We're going to talk about it in class like we did previously about using 0.7 versus using 2/3. All right, so we're going to graph this and hopefully we're going to see that decay function. Again, some of our values are going to be a little too big, but we can kind of estimate where our -1 would be. And then 0 is at 15. And 1 is going to be at 10.5 and 2 is at 7.4. So we see our graph declining, and that's great. That's exactly what we want to see happen. All right, 3 says a fully inflated raft loses 6.6% of its air every day. The raft originally contained 4,500 cubic inches of air. Write an equation to represent the loss of air during the using the general equation for decay. So we're thinking y equals c times 1 minus r to the t. So we have y equals, well, we start with our 4,500 cubic inches, 1 minus, and we have a percentage, so 6.6%, we're going to move decimal place over 1, over 2, so we're going to have 0.066 to the t. Go ahead and simplify by subtracting this inside the parentheses, and we get 4,500, and what do we have in the parentheses? 0.934 to the t power. There is our expression. We knew that this was decay because of the word loses. So anything that is going to tell you that something is decaying, decreasing, it's losing, it's a decay problem. All right, estimate how much air will be lost after 7 days. So we're going to take our function that we just created, and we're going to plug in 7 in for our t. Go ahead and putting that into our calculator. We find out that we have 2,790.23 cubic inches of air. And that's how much is left after a week. Okay, so here, number 4, it's again, it's a word problem. And here it says, write the equation, and then assuming that the trend continues, estimate the population in 2013. So it's not going to give you an A and a B to ask to do these, but I'm very confident that you'll be able to come up with the equation, and you're going to be able to predict an estimation for population in 2013. Go ahead and finish up 4, and then I want you to try 5. It's another, 5 is missing. Well, I guess we'll be doing 5 together. We'll see you guys then.